Good evening. Yeah. So in the last class we have learnt about the definitions, basic concept about current, potential difference, all those things, isn't it? And we have seen about the schematic circuit diagram, electric circuit diagram. And then we saw the different symbols for electrical components, right? Now today we are going to have a further study on this potential. That is, we just want to know, is there any relationship between potential difference across a conductor and the current through it? Potential difference across a conductor and the current through it, right? To understand that, we are going to have an activity, right? A small activity. This activity is very easy to do. Even at home also you can do, if provided if you have got a multimeter or a ammeter and voltmeter, right? That way it will be very easy for us to perform. Let us see how to perform this activity. Now what is required? We need a nichrome wire. Nichrome wire. What is that nichrome wire? There is a new name here. Usually instead of ordinary conducting wire, we are using a nichrome wire. Yeah, nichrome is nothing but, the word itself we can see that, Nichrome, isn't it? That Ni, nichrome, is an alloy of nickel, chromium, manganese and iron. 4 metals are there. An alloy of 4 metals. Right? This may be a multiple choice question. Sometimes they may ask. Because this nichrome is used as a resistor here, from which we are going to find out the potential difference. Okay? So, we are going to set up a circuit consisting of a nichrome wire. We name this nichrome wire as XY. The ends of this wire is named as XY. Right? Say, for example, they have given a length of, say, it can be 0.5 meter or 50 centimeter. Right? So, and an ammeter, voltmeter, and a set of 4 cells, which we call it as battery. That battery consisting of 4 1.5 volt cells. Usually, you would have seen the circuit diagram. Already we have seen the schematic diagram, circuit diagram. But actually, in the laboratory when you do, the practical connections will be somewhat different from what we see in the circuit diagram. Now for our purpose, convenience, I have just shown you in the lab how we can connect the different components here. Look at that. This is the actual connection. How the connection will be. Right? See, this is the battery which is consisting of 4 1.5 volt cells. And this is called a nichrome wire. Okay? Wire will be like this, like wound coil. Right? And this is the ammeter, and this is the plug key, and this is the voltmeter. This is how we have to connect. And remember, always this voltmeter should be connected across the wire. Wherever you want to measure the potential difference, it should be connected one end to the other end. It should not be in series. You can see that the ammeter, the plug key, the cells are in series connection. But always this voltmeter should be connected across the component, wire resistor. Then only you can find out the potential difference between these 2 ends. Right? So this is the actual connection when you are going to perform the activity inside the physics lab. But if you just, by noting down this, if you want to draw a schematic diagram of these components, it will be looking like this. You can see that this is the electric circuit or schematic circuit diagram for studying the Ohm's law. See, each cell is represented by long line and short line. So each one is 1.5. And this end positive and this end is negative. You know that when they are connected in series cells, you have to connect as end to end. That is positive to negative like this only. As we have seen in the torchlight, how we put the cells inside the torchlight. In that way you have to connect that. Right? From that, one end is connected to the nichrome wire, the other end is connected to the positive side of the ammeter, the negative to the key, and key to the negative of this cell. And across this we are connecting the voltmeter. And note that this positive is connected to the positive of this. Okay, positive to positive. Because 2 terminals will be there. one red color and one black color usually. This red color is always indicated as negative and black color usually positive. So that way by looking at that you can just connect that. Right? Symbolically we can represent. Right? This is the circuit diagram for studying the Ohm's law. Now how simple it is you can see. First we are going to use, instead of 4 cells, we are going to use only one cell as the source of EMF in the circuit. Right? So we know that the cell is the one which is providing energy for the electron, so that is source of EMF, so that the electrons will start flowing. Once we connect the plug key, right? Usually when you are starting the practical, the plug key should be plugged it out. It should be an open circuit. Only when you are ready with the tabular column, you have to plug the key, and then we have to note down the reading. How to note down the reading? We have included only one cell. By the time, the EMF will be 1.5 volt. So as the current flows through that, the ammeter will have a deflection, and accordingly the voltmeter which is connected across the nichrome wire will also have some deflection. So by the deflection of the needle, we have to note down the reading. But if it is digital meter, it will show the exact number easily. But usually for lower level like 9th standard, 10th standard level, we usually use this analog meter, because you have to know how to calibrate, no? Because how many divisions are there, what each division is indicating, how much each division is indicating, like that, you have to understand that. So that we will use this analog meter only. Say for example, I have taken one reading for you. The current through the nichrome wire is 0.2. That is, the ammeter reading is reading as 0.2 ampere. And simultaneously I have noted down the potential difference, that is voltage across the nichrome wire is 0.4. Right? The current through the circuit is 0.2 ampere. The potential difference across the nichrome wire is 0.4 volts. So this is the first step in the experiment. Now as we have seen that, I have indicated by different color, one cell we have included for the first step. Naturally, what will be the second step? You are going to add one more cell. Right? So 2 cells will be introduced now. When 2 cells are connected, 3 volts will be there. That is 1.5 plus 1.5. 3 volt EMF will be supplied by the battery. Now again we have to note down the current in the circuit using the ammeter. It is showing 0.3 ampere. And the voltage across the 2 ends of the nichrome wire is 0.6. But this is only for example purpose. It may not be always same thing. Depending upon the wire what we are using, depending upon how much current, how many batteries we are connecting, these readings will be varying. Okay, so for example I have taken it is 0.3 and 0.6. Now next one will be, we are going to add one more. So 3 cells will be there now. So how much 3 cells will provide EMF? How much will it provide? What will be the voltage? That is, what will be the EMF supplied by these 3 cells? No. What could be the EMF supplied by these 3 cells? When 3 cells are connected, what is the EMF? Yes? Are you able to hear? Tell me. Such a big arithmetic I have asked, no? Each one cell is having 1.5 volt. 3 cells means how much will it supply, man? That's all. For that you are taking this much time. Okay. So, and 3 cells are connected, it will provide 4.5 volts. Okay. Now, again what we have to do, when you are connecting 3 cells, again when you are connecting 4 cells, you have to note down the readings which is shown in the ammeter as well as the voltmeter. And then after this, we are going to find out the ratio of this potential difference to the current. That is V by I ratio. Right? V by I ratio. So V is 0.4 and I is 0.2. So divided by 0.4 by 0.2 is nothing but 2. So if I calculate like this, you can see that all the ratio for a first cell, for 1 cells, 2 cells, 3 cells, 4 cells, the ratio is seem to be the same thing. The ratio of V by I is same, 2, 2, 2, 2, right? Now, using this value, yes, right, we are going to plot a graph by taking current in the x-axis and the potential difference in the y-axis. Whatever the reading we have taken as 0.2, 0.3, 0.4, 0.5 as the current in the x-axis and 0.4, 0.6, 0.8, 1.0 as the potential difference. Whatever we have got the reading, we are going to plot a graph, right? So from that graph, what we are going to analyze, let us see. Now we can see that this is the graph showing current in the x-axis and potential difference in the y-axis. Now you can see that how to plot, you know that 0.2 and 0.4. So 0.2 in the x-axis and 0.4 in the y-axis. Similarly, 0.3 in the x-axis, 0.6 y-axis, 0.4, 0.8 and 0.5, 1.0. Right? This way, when you connect all these points, you can say that you are getting a straight line. Right? So which is passing through the origin. Yeah, which is passing through the origin. Right? So the graph also will show you when it is a straight line which is passing through the origin, it means that the difference, the ratio of V by I for all the 3 points or 4 points will be same because they are equidistant from both the axes, isn't it? So from that we can say, not only from the graph as well as from the tabular column, that V by I is a constant, the ratio is a constant, right? So from that graph, yes, okay. From that graph, by using this kind of experiments, this great scientist, German physicist, George Simon Ohm, he only performed that experiment and found that a relationship between the current flowing in a metallic wire and the potential difference across the terminals. He only established the relationship, right? After that only we are able to see that, we are able to perform these kind of experiments, right? So, you have to remember the name also, George Simon Ohm. He only found the relationship between the current and the current flowing through a conductor or metallic wire, whatever you call, and the potential difference across the terminals. So what did he say? This is what we call as Ohm's law, right? So this is what we call as Ohm's law. The potential difference across the ends of a given metallic wire in an electric circuit is directly proportional to the current flowing through it, provided its temperature remains the same. There is a condition, right? There is a condition. You have to remember, the condition is the first preference should be given at a constant temperature, you have to say. Right? Usually, when you go to higher classes, the statement will be like this. At a constant temperature, right, the potential difference across the two terminals of a metallic or conductor is directly proportional to the current flowing through it, right? That means V is proportional to I. This is what it says. V is proportional to I. So by using this expression, you can remember the Ohm's law. What is the condition? This is the important condition. Temperature remains the same. Why? Because as the temperature increases or decreases, it may not be applicable. And also, the current should be a steady one. Current should be a steady current, right? Yeah, it may be increasing or decreasing depending upon the temperature. And you may be quite surprised to know that you may be studying later classes that there are conductors which will conduct a current without any resistance, that is at zero resistance at a very low temperature. They are called superconductors, which we'll study in the later classes. Okay, at present you remember that in the statement the temperature should remain the same. So I'll repeat again I'll state the law again. The potential difference across the ends of a given metallic wire in an electric circuit is directly proportional to the current flowing through it, provided its temperature remaining the same. This is what we call as Ohm's law. So this Ohm's law can be remembered by using this triangular symbol easily, right? VIR, Vir. Param Vir Chakra, no? Vir Chakra, like this. Right? Remember like this. So V is proportional to I. Whenever there is a proportionality symbol, when you want to remove the symbol, we will just V by I, we will take it as a constant. When we have seen the tabular column also, that it shows that V by I is a constant, right? And here we have given the constant a name, a symbol. It is represented as R. So from this we can say V by I is equal to R, or V is equal to IR, or from this we can say V is equal to IR, or R is equal to V by I, or I is equal to V by R. By taking this triangular symbol, you can say 3 variables are given. If 2 are known, the third one can be found out. So to remember that only, we have given this V, I, R. Right. So these formulae you have to remember. V is equal to IR, I is equal to V by R is equal to V by I. Because we are going to use this for solving numerical problems. Okay. Right. Now, here we said that R is a constant, isn't it? The constant name is given as, symbol is given as R. And this R, for a given metallic wire at a particular temperature is called a resistance. I said temperature remaining constant. So at a particular temperature, for the particular metallic wire, that R is a constant. That R is called a resistance. So what is resistance? If there is a question, we have given that R is a resistant, the symbol is there. But what is a resistant? It is nothing but, the word itself says that resist. So what is this resisting, opposing? It is opposing the current. Opposing the current means current is nothing but flow of charges. So resistance is the property of a conductor to resist the flow of charges through it. That is the definition you have to remember. So if somebody says what is resistance, means you can say that it is the property, specific property of a conductor to resist the flow of charges through it. It will always resist the flow of charges. That is why when you pass the current, you will not get the free flow of electrons, charges through it. Something is resisting that inside. Right? So that resistance is only indicated by letter capital R. And it is, usually we know, resistance is a physical quantity and it has got a unit also, which is called OHM, ohm. Ohm. Okay? And it is represented by a letter, Greek letter, ohm. Symbol is there, and letter wise you can write as OHM, ohm. Okay? So this is the definition you have to remember. Right. Now, as we have seen that according to this Ohm's law, in the triangle we have seen, R is equal to V by I. That constant, the resistance is equal to V by I. Right. Now what we are going to do, by using this formula, we will define what is the unit of resistance. Just now we have seen the unit of resistance is ohm. So how to define 1 ohm? When will you call that a resistor or a metallic wire has got 1 ohm? Right. So simply by using this formula we can say when voltage is equal to 1 unit volt, when current is 1, then R will become 1 by 1 will be 1. So if the potential difference across the two ends of a conductor is 1 volt and the current through the wire is 1 ampere, then the resistance of the conductor is 1 ohm. Or we can put it in another way, a conductor is said to have a resistance of 1 ohm if the potential difference across the ends of the conductor is 1 volt and the conductor is carrying a current of 1 ampere. You understand? Yes? Can you repeat that? Yeah, can you repeat it? Define 1 ohm. Can you repeat? Define 1 ohm or define the unit of ohm, that is unit of resistance. I'll change this. Come on, now tell me. Yeah. 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 Then the resistance of the conductor or a metallic wire is said to be 1 ohm. Very good. Right. So, from this, it is quite obvious from the equation that I is equal to VR we have seen, V by R we have seen, right? Now, we can see that as this R is in the denominator, right? And V is in the numerator. Always, when it is in the numerator, we have to say that I is directly proportional to V. And when it is in the denominator, we have to say I is inversely proportional to R, right? That means when I increases, V increases. But when I increases, R decreases. Or when R increases, I decreases. Right? When R increases, I will decrease. That means inversely proportional. So that the current through a resistor is inversely proportional to its resistance. That means when a current is flowing in a conductor, if the conductor has got more resistance, naturally what will happen? Less amount of charges can flow. So current will be less. If the conductor is offering less resistance, more amount of charges can flow, so that the current will also be more. Isn't it? That means now we can say, for example, if the resistance is doubled, what will happen? See, if the resistance in place of R, I say if it is 2R, so I is equal to V by R we say. If R is equal to 2R, right? That means if resistance is doubled, now substitute the value here, what will happen? I is equal to V by 2R, isn't it? That means actually earlier it was V by R, now it has become half of that. That means half of V by R, which is V by R is nothing but I. So current will become half of that. So if resistance is double, current will get halved, half of that. It will remain half of that. So that shows that as the resistance increases, the current will also be decreasing. It will not be increasing, it will be decreasing. So that is the point you have to remember. Right. Now, in many practical applications, when you are using electrical components or different instruments, it is very much necessary to decrease the current in an electric circuit. So, how can you decrease the current when you are doing practical, for example, right? So, sometimes we need to increase the current, sometimes we need to decrease the current, right? So, how can we do that? Can you guess it? How can you increase or decrease the current in a circuit? No. That is one option, okay. But I said that when you increase the voltage or, okay. Suppose if you have got only one battery, right? There is no other option. When you are using a battery, constant battery, in the battery you cannot take the cell. Here we are using cells so that we are removing. But in the battery, if you have got only one battery, how will you increase or decrease the current? Yes? Exactly. That means you have to use a resistor. But that resistor, if you are using a metallic wire, that metallic wire will have a constant resistance. We cannot change that. Every time we cannot replace a wire with a different resistance. For that only, we are using a variable resistor, what we call as variable resistor, a component used to regulate the current without changing the voltage. Okay, without changing the voltage, so without changing the battery, which is called a variable resistor. So this is the variable resistor, right? But here we are using rheostat. In the laboratory, if you go to your laboratory, school lab, there you will see that to change the resistance, we often use this rheostat. Already we have seen the symbol. This is the symbol for variable resistor, and this is the symbol for rheostat. Okay, so a rheostat or variable resistor is used to control the or regulate the current flowing through a circuit, right? Okay, now there is another activity, right? In this activity, we are going to take a nichrome wire, a torchlight bulb. You know the torchlight bulb will be very small. After all, we are using two batteries, two cells only for a torchlight bulb, isn't it? If you connect two batteries, the bulb will glow. If you connect more battery, what will happen? The bulb will be fused. The tungsten will get cut. Such a small bulb it is. And again, we are taking a 10 watts bulb. 10 watts bulb will be like your bedroom light bulb. right? Or your bike bulb, which will have 35 watts or 10 watts, different wattage bulbs are available. Here we are taking a torchlight bulb, a 10 watts bulb, and an ammeter which is having a range of 0 to 5 amps, right? And a plug key and some connecting wires. So using this, we are going to set up an electrical circuit. Okay. So we are going to use, as usual, 4 dry cells of 1.5 volts. So what is the total EMF now? 6 volts. 4 into 1.5, 6 volts. And it is connected in series with the ammeter, leaving a gap. Here we are not going to close the circuit. We are going to keep it as an open circuit. Let us see how. See that? This is the actual circuit. Yeah, there are 4 cells, each one of having 1.5 volts, 1.5, 1.5, so that's 6 volts battery. Okay. Now it is connected in series with the ammeter and a plug key, and it is kept open. There is a gap. Without completing the circuit, it is kept as open, and that open gap is named as X and Y. Right? Here there is a bulb. This is the 10 watts bulb, and this is the torchlight bulb, and this is the nichrome wire. This is only example. I said the nichrome wire is wound on a wooden piece, but usually in the lab you can see that it may be wound on a plastic, or it may be kept bare. It may be any wire, right? Just for practical purpose, we are wound on that wood. It may be of any shape or any length, right? So these are the different components we are going to use for this activity. Now let us see how these components are connected and represented schematically as a diagram. You can see that this is the ammeter, and this is the gap we have kept X and Y, and the positive side of the ammeter is connected to the positive terminal of the battery, and negative terminal to key, and the key to Y. Okay, so this is the exact circuit for studying this activity. Now what are we going to do? First, in the gap XY, we are going to connect the nichrome wire, right? So you know that nichrome wire will offer some resistance, right? Now we are going to plug the key. Remember that already I have told you, when you are connecting that, the plug key should not be inserted. It should be kept aside. After connecting the nichrome wire only, we have to put the plug so that the current will start flowing. Now after that, we have to note down the ammeter reading, right? Okay, now we take out the plug key. The current will not flow. At that time, we have to replace the nichrome wire, keep it out, and take the torchlight bulb, right? So as the current flows, what will happen? When you plug the key, the torchlight bulb will glow, right? Now at the time, we have to note down the ammeter reading. Again, in the third step, we have to repeat the same thing by using the 10 watts bulb. We have to replace the torchlight bulb with the 10 watts bulb in the gap between that is gap XY. For all the 3 steps, we have to note down the ammeter reading. Do you think that in all the 3 steps, the ammeter reading will be same? Do you think so? Yes? In all the 3 steps. Why? Can you tell me why? Okay. See, in the first one we are using the nichrome wire. In the second one we are using a torchlight bulb. You know that torchlight bulb, inside the bulb there is a filament inside. That filament is made up of tungsten, we say. Tungsten. Right? And the third one is 10 watts bulb, which will be, the tungsten will be somewhat thicker. In the second bulb, the torchlight bulb, it will be very thin. In the 10 watts bulb, it will be somewhat thicker. And this nichrome wire is very thick, you know that. Now, in all the 3, if you note down that the ammeter reading may not be same. It may be different for different components. Right? You can also repeat that with using different materials. not only by using a nichrome wire, you can use copper wire, you can use iron, right? You can use some other bulb, and you can observe in each case, you can observe the reading that it will never be same. For each component, right, the current is different for different components, because each one is offering a different path for current. That means each one will have a different resistance. For example, if we take nichrome wire, it will offer more resistance for the current. But if we take a torchlight bulb, it will offer less resistance for the current, right? So, because of the difference in resistance, what will happen? They will have different amount of current flowing through that. They will allow different amount of current flowing through that. Isn't it? So, we know that the most of the electrons in the electric circuit only constituting the electric current. So, if they are not allowing enough amount of charges or electrons to flow through that, accordingly the current will be. If it is allowing more amount of charges, it will allow more current. It means that, so depending upon the component, how much resistance it is offering, the current will also be varying. Isn't it? So, the electrons which are flowing through a conductor, they are not completely free to move within a conductor. We say that a conductor is the one which will allow the electrons to flow through it, isn't it? But though it is a good conductor, it is not free, it is not allowed to move freely. They are restrained, or the movement is restricted by the attraction of atoms within the conductor, right? Because the atoms are there in the conductor, the atoms are there, the electrons in the atoms are moving, right? They are randomly moving. Throughout the conductor, electrons are randomly moving, you know that. Due to this movement of the electron inside that, what will happen? These electrons are not allowed freely. Okay? So, they are retarded. The movement of the charges are retarded by the resistance. To overcome this resistance only, we are providing the external EMF so that the electrons are flowing. But to overcome, I said, there is a limit with which each metal or each conductor is offering some resistance. That will be varying for different components. It may, whether it is iron or whether it is copper or nichrome or manganese, but different materials will offer different amount of resistance for flow of charges through that. Okay. Now, when you classify that based on their resistance towards offering towards the flow of charges, right? We can say a conductor, good conductor or a poor conductor, or what we call as insulator or resistor. We can classify them accordingly. Let us see. The first one is a component of a given size that offers very low resistance is called a good conductor. What is a good conductor? Give examples. We can say any component or any material of a given size that offers very low resistance is called a good conductor. You can say examples are metals and alloys. Metals and alloys are the very good conductors. They offer very low resistance. So that is why we are using it for transmission purpose. So that it can carry the current without much loss. Right? And if it is offering appreciable resistance, more resistance, then that material is called a resistor. So what is a resistor? Means you have to remember that what is resistance, what is a resistor. Resistance is the property. Resistor is a component or a conductor. Okay. So a component or a conductor or a material which is having some appreciable resistance is called a resistor. And similarly, a component of identical size that offers higher resistance, if it is offering more resistance, is called a poor conductor. Okay, this is appreciable and more. There is a difference you have to note down. Appreciable means this can be noted down, right? Okay, so we know that we can say that this material will offer this much resistance like this, which is called appreciable, not very low, more than the low, because low resistance is offered by the metals and alloys. They are good conductors. So appreciable resistance, if it is offering, we call it as a conductor, that is resistor. If it is offering very high resistance, then we say it is a poor conductor. For example, you take pure water. Through pure water, electricity will not flow. Charges will not flow through a pure water. So that is a very poor conductor. Okay? And similarly, even if it is providing more resistance, high resistance, then we call it as an insulator. In insulator, current cannot flow through at all. Say, for example, glass, wood, quartz, rubber, all these materials, they are all called insulators. They offer high resistance, very high resistance. They are called insulators. So, there are classification. Insulator we have seen a poor conductor, we have seen a resistor, we have seen a conductor. So, based on the examples, they may ask you to pick out which is the conductor, which is a poor conductor, which is a resistor, insulator, like this. Okay, just for you to remember the examples, so that when the question is asked, we can pick out the answer correctly. Okay, and there is one more activity. This activity is also very simple, that we are going to have a circuit, electric circuit consisting of a cell, ammeter, and a nichrome wire of length L and a plug key. We have taken the length, we have specified the length of the wire as L. Okay, nichrome wire of length L. We can see that this is the first diagram. You can see first, second, third, fourth. We are using 4 different wires. Okay, first wire is from here to here, usual one. The second wire is bigger one. The third one is somewhat thicker, and fourth wire. So all the 4 wires, right, we are going to use in the circuit. Now what are we going to do? As usual, we are going to plug the key and note down the current in the ammeter. That is our aim. But what is the important thing here? Instead of one nichrome wire, we are going to replace it with the different wires, so that we will note down the ammeter. Right? For example, the first one, after noting down the current in the first wire, first nichrome wire of length L, we are going to replace the same nichrome wire with another wire of length which is having the same thickness but twice the length. That means 2 length. I have shown you. See that this is the length we have seen. This is 2L, 2 times the actual length. Okay. Again, we are going to note down the ammeter reading. Yeah. Then in the third one, you have seen that the third one is the somewhat thicker wire. Right? The same first wire is going to be replaced by a thicker wire of same length. Now, you know that a thicker wire means it will have large cross-sectional area. That means thick means thin and thick. Thick means somewhat the cross-section area is somewhat bigger. Right? Again, for this case also, we are going to note down the current. So, in all the 3 cases, we are going to note down the current. Now, in the fourth one, instead of nichrome wire, we are going to replace it with a copper wire. Again, it is having the same length on the same area of cross section of the first nichrome wire. In this case also, we are going to note down the current. So, we have taken 4 wires. One wire is the usual nichrome wire. The second wire is having twice the actual length. The third wire is the thicker wire than the previous one. But the length is same L. And the fourth one is also same length, same cross section area, but copper wire. In all the 4 cases, we are going to note down the current. Right? Now, we can compare the current. In all the 4 cases, we can compare. Is that current depending on the length of the conductor? Is it depending upon the area of cross section? Because we have used in the second one thick wire, third one in the thick wire, second one twice the length, and the fourth one different material. So 3 cases we have seen. Okay, first one is length is a factor. Second one, that is third one, area of cross section is the factor, and fourth one, material is the factor. 3 factors we have seen. In all the 3 factors, we will check it out whether the current is changing. Yes, it was observed after performing the experiment. You can observe that the resistance of the conductor is depending upon 3 important factors. What are they? One is it is depending upon length. That means if the length is more, it is offering more resistance, so the current will be lesser. Okay. If it is cross section, that is if it is thicker wire, the current is more. Current can flow, more current can flow, or more resistance will it offer. Can you say? In what way will it be varying? If you increase the area of cross section, do you think that it will offer more resistance or it will offer more current? Can you say? Do you think that it will offer more resistance? Okay. And also if you change the material, instead of nichrome, if the copper is there, so depending upon the material what we are using, the resistance will also be changing, isn't it? So after that again, precise measurement, they have shown that the resistance of a uniform metallic conductor, that means the area of cross section is uniform everywhere, that is called a uniform metallic conductor. And from that they have understood that from the experiment they have performed, they have understood that the resistance is directly proportional to its length. That means as the length increases, resistance is also increasing, and inversely proportional to the area of cross section. If area of cross section is more, resistance is less. If area cross section is less, resistance is more. Inversely proportional. Because if the area is more, it is like a water tube, water pipe. If area is more amount of water can flow. It is similar to that. If less amount of area means less amount of water. Similarly, it is after all flow of charges. So the resistance is inversely proportional to the area of cross section. So from there, the two statements we have taken. One is the resistance is directly proportional to the length, and resistance is inversely proportional to area of cross section. Inversely means 1 by A. These are the two statements precisely they have found out from the experiment. Now they are going to combine that. When you combine these two equations, what will you get? R is equal to this 1 into L will become L and A, L by A. R is proportional to L by A. Right. Similarly, I told you whenever you are removing this proportional symbol, you have to add a constant here. So R is equal to rho. We are adding a special symbol here, rho into L by A. Where rho is here is called a specific resistance or electrical resistivity. You remember that the symbol rho in physics, hereafter you have to remember that this is representing the specific resistance or electrical resistivity. Specific resistance or electrical resistivity, both are same. Right? It should be read as rho. Constant of proportionality, rho. It's called a specific resistance or resistivity of material of a wire. Whatever material, whether it is a copper or nichrome, that will have a specific resistivity. Okay? And you can see the unit of this resistivity, rho. How to find out the unit of resistivity? From this expression, R is equal to rho into L by A. I want rho only. So rho is equal to, cross multiply that, R into A by L. R into A by L. So rho is equal to RA by L. So R is nothing but resistance, ohm. Area of cross section, A is nothing but square meter. And the length is expression meter. So this meter and square will get cancelled. So what is remaining now? Ohm meter. So this ohm meter is nothing but the unit of resistivity. And it is a characteristic property of a material. It means that all material will not have the same resistivity, but the resistivity of materials will be differing from one material to another. That is what it says, last point says. Okay, you have to remember these two formulae. R is equal to rho L by A and rho is equal to RA by L. From this only we are getting. Okay, that means by remembering this, R is proportional to L and R is proportional to 1 by A, we are combining that, removing this proportional symbol, adding this constant rho, and then we say rho is equal to RA by L. Because we are going to use this in the numerical problems for solving. So remember that rho is equal to RA by L. Okay. So the last part we'll see. This is the last part of this chapter. The metals and alloys. When you are comparing the resistivity, we are talking about the resistivity here, isn't it? the metals and alloys, they will have very low resistivity in the range of 10 power minus 8 to 10 power minus 6 ohm meter. Remember the range also. You have to remember exams, they may ask the range also. Metals and alloys, they have the low resistivity, so that they will allow the flow of current easily. 10 power minus 8 to 10 power minus 6. Because they are having low resistivity, they are called good conductors of electricity. On the contrary to that, yeah, I've told you, from this expression we can say, right, from this expression I said, rho is equal to RA by L, isn't it? By this expression only we can define, of course, I don't think that you got the definition for that, even then I'll tell you. Rho is equal to RA by L we have seen, right? Yeah. Resistance is different, resistivity is different. Specific resistance is a specific resistance or resistivity. See that the specific resistance of a material of wire. Suppose if you want, you are asking the definition for resistivity. That means resistivity is 1 ohm meter I want. If I want 1 ohm meter, what should I do? I should take all these things as 1. R should be 1, A should be 1, L should be 1. Yes or no? So, by using this 1, 1, 1, I will define what is resistivity. The resistivity of a material of a wire, right, is the resistance offered by a conductor of unit area of cross section and unit length, per unit length. Okay? The resistance offered, see, when I say that these are 1, see for example, I will take like this. I say rho is equal to RA by L. This is the formula, isn't it? I want that rho is equal to R. If I take rho is equal to R, that means A is equal to 1, L is equal to 1. Do you understand? So I will say simply, resistance is nothing but resistivity. Resistance offered by a conductor is resistivity. When that conductor is having 1 square meter, area of cross section as unit cross sectional area and a unit length. Okay? So simply in a nutshell I will put like this. A conductor is having 1 meter length and the area of cross section of the conductor is 1 square meter. Okay? That conductor is offering resistance. That resistance is called resistivity. Do you understand? Do you understand? Yeah? So I will repeat just finally, the resistance offered by a conductor of unit area of cross section and unit length. Resistance offered by a conductor of unit length and unit area of cross section is called a specific resistance or resistivity. That is what it says. Of course, this definition is not there in your book. It is only for higher classes. At present, remember that rho is here nothing but resistivity and the unit is ohm meter. And I have told you how to get this ohm meter also from this formula. And this is what it says. Okay. And we have seen the classification also. 10 power minus 8 to 10 power minus 6 ohm meter. If it is providing this much of very low resistivity, they are called good conductors. Metals and alloys, they are good conductors. Insulators will offer very high resistivity, which is in the range of 10 power 12 to 10 power 17, very high ohm meter, right? And both resistance and resistivity of a material, as we have seen in the beginning of the Ohm's law, they will vary with the temperature. As the temperature increases, resistivity will also increase. You know that why? Can you guess why? Why the temperature, when the temperature increases, resistivity is increasing, resistance is increasing? Yes, quickly. Okay, suppose there is a ground, okay, where there are some 1,000 people are there, 1,000 students are there, and you just want to go through right? From one end to the other end of the ground, you are going to pass through those persons, right? If they are just standing in a row, right? If they are practicing a march past, for example, or drill, and there may be a gap so that you can easily pass through them and reach the other end. Instead, if all the 1,000 students or 1,000 people are running here and there, zigzag movement, and you have to pass through, okay? Is it possible, do you think? Is it that much easy, do you think? No. Similarly, when at a high temperature, the internal energy of the conductor, that is, the electrons will have more energy, right? They will be moving. The free electrons are free to move inside the conductor here and there. There will be zigzag movement, right? At the time when you want to push the electrons through them, it's very difficult, isn't it? So that it will offer more resistance. And when you cool down the conductor, when you decrease the temperature of the conductors, the electrons will lose their energy, heat energy, and they will calm down, right? So when you decrease further to zero, below zero, so that the conductor will not offer resistance at all at a particular temperature, right? There is a transition temperature for every material, every metal. At that transition temperature, the conductor will become a superconductor, and that will be a perfect conductor where it will not offer resistance at all. It will offer zero resistance. Okay, so that is why we say as the temperature increases, the resistivity is also increasing. Okay, right. So these 2 points are there. You have to remember that. We will wind off with this point. As we have seen that the resistivity of alloy is generally higher than that of the constituent metals. Suppose if you take a nichrome, separately if you take nickel or chromium or iron, they will offer different resistance. But once they are combined, right, the resistivity of this alloy will be lesser than the constituent materials, right? And also they do not oxidize easily at high temperature. These are the two important points which may be asked in 3-mark question. Why are alloys used for preferable for electrical devices or heating devices? That may be a question. These are the 2 points you have to remember. The resistivity of alloy is higher, generally higher than that of the component metals, constituent metals. Okay. So that if it is offering more resistivity, it can withstand more current. And similarly, they don't oxidize. That means oxidize means combining with oxygen, burning at high temperature. They will not easily burn at high temperature. That is why they are commonly used in electrical press, heating devices, iron box or toaster. In all these materials, we are using, instead of a single metal, we are using alloys. Okay, these are the 2 reasons. Right, and similarly, if you take a tungsten, this tungsten is exclusively for electrical bulbs. In the middle, you can see that this is called a tungsten filament, right? And it is offering very low resistance, right? And a high melting point. At a high temperature only it will melt. When a very high current flows only, it will melt. So that it is used as a filament for electric bulbs. Whereas this copper and aluminum, they are used for transmission lines because they offer very low resistance for the flow of current. That is why they are used as a transmission lines, cables for overhead cables for transmission purpose. Okay. So with that we will stop, and in the next class we will solve some numerical problems and then we will proceed further. Okay. Thank you. Yeah.